Hello and welcome back to Physics Galaxy. And this is lecture number 8. And today we're going to do some miscellaneous examples related to the topic of method of images. And this is our question number 1. And the question says, in the method of images, which primary condition is used to place the image charge? A. The image charge is placed to satisfy the Laplace equation. B. The image charge is placed to satisfy the Dirichlet boundary condition. C. The image charge is placed to satisfy the Newman boundary condition. Or D. The image charge is placed to satisfy the uniqueness theorem. So remember when we did some problems related to the method of image. Suppose we had an infinite grounded conducting sheet V equals to 0. Suppose this was our charge Q. Suppose this was our charge Q. Okay, so charge Q. Then we put image charge. We put image charge minus Q here, right? To satisfy what? To satisfy the V equals to 0, right? So this is one point P1. We make sure that this point P1 or this point P2 or all points on this infinite grounded conducting sheet was 0. Okay, the potential on each point was 0. Okay, that's we can say make sure that the all points satisfied the condition V equals to 0. But what is this condition? This is the Dirichlet boundary condition. So option B, that is the image charge is placed to satisfy the Dirichlet boundary condition, right? Now coming to question number 2, and the question number 2 states a point charge q is placed at a distance d above grounded infinite conducting plane. If a second identical charge q is introduced at the same height d but at a horizontal distance 2d from the first charge, what will be the force between the two charges due to their respective image charge? So we have a situation like this. So suppose this is my infinite grounded conducting sheet. Okay, V equals to 0, and suppose I have a charge q. I have a charge q. This is a charge q. This is a charge q. Okay, and which is at a distance of d. So this is d distance, right? Then if a second identical charge q is introduced at same height पे हमारे पास एक और charge है q. Okay, d, but with a separation, horizontal separation of 2d. So 2d horizontal separation. So this is the 2d horizontal separation. And like that, the force between two charges due to their respective charge. Now there will be image charges. So we'll put our image charge here. So this is our first image charge minus q at the same separation. So this will be at the distance of d. Okay. Similarly for this, we'll have again minus q at d. Okay. Now what we have to find? We have to find what will be the force between the two charges due to their respective image charge. That means we have to find the force on this charge due to the image charge of the second charge. So let's find it out. Now we know this distance, we know it simply is this it is capital D. So capital D equals to, that is the distance from this real charge to the image charge of the second charge. That will be under root of this is 2d and this is also 2d. So 2d whole square plus 2d whole square, which equals to under root of this is 4d square, 4d square, 8d square. We can simply write 2 root 2d. Okay. Now what will be the force? Okay, force will be given by simply 1 by 4 pi epsilon, or instead of 1 by 4 pi epsilon, we'll write simply k times the product of the charges, that is minus, or because we have to find the magnitude, so we'll not include the minus sign. So this is q times q, that is q square divided by the d square. Okay, d square is this d square, this square, this square, this square. So we'll get simply 4, or 4 to the 8, 8d square. So 8d square. So it's option number B, right? Okay. Now let's move on to problem number 3. Problem 3 states that a charge Q is a charge Q is located at 00D above a grounded infinite conducting plane lying in the XY plane. What is the total induced surface charge on the conducting plane Y? Okay. Option A, minus Q due to the requirement of the zero potential at the surface plus Q as induced charge must cancel the field above the plane minus 2Q from the Gauss's law for the field above the plane plus 2Q to counteract the image charge field. Okay. So remember, suppose this is my infinite grounded conducting um, sheet, okay, in the XY plane, and I have my image charge here. So my Q. Okay, at a distance of 0, 0, D. So we did this problem, and we also found that we have to put our image charge here minus Q at distance of 0, 0, minus D. Right? And then we also calculated the total induced charge. Total induced charge was minus Q. Okay, Q induced was equals to minus Q. Okay, and we also said that it was, if we want to find the distribution of minus Q, it will be like this. Okay, so minus Q will be like this. Why? Because this Q will uh, exert force on the electrons which are present on this metallic sheet. Okay, and that they will be pulled towards this plus Q. Okay, this real positive charge. Okay, so we have this kind of distribution of negative charges, and this whole charge will be equals to minus Q. This whole charge will be equals to minus Q. Okay, minus Q. Sorry, let me change the color. Minus Q. Okay, minus Q. But because this is at potential V equals to zero, there will be, because this has a potential zero. Okay, it has been grounded. So this grounded sheet will collect positive charge. Okay, because it has to neutralize. Okay, and there will be also positive charge. So that positive charge will be uniformly distributed also. Okay. But the induced charge will be minus Q. Okay. Induced charge will be minus Q, and if we want to find the total charge, that will be zero on the board. So minus Q gives the requirement of zero potential at the surface. Okay. Now let's move on to the third question. So the third question states: consider two grounded parallel conducting planes separated by distance L. A point charge Q is placed midway between the planes. How many charges are required to solve for the potential everywhere in this configuration, and where will they be located? Where will they be located related to the original charge? Okay. Okay, so we have configuration like this now. We have two infinite grounded conducting planes. Two infinite grounded conducting planes. Okay, so this is grounded, this is grounded, and separation is L between these planes. Okay, and my image charge is midway between the planes. Okay, so this is my real charge is Q here. Right now, what we do in mathematical images, we satisfy the digital boundary condition. Okay, so I have to balance out that V equals to 0 for this plane and V equals to 0 for this plane also. Okay, so let's put an image charge, first image charge. Okay, so this is our minus Q. So this minus Q will set this minus Q, and this plus Q will satisfy all the points. Okay, and we'll make sure that these all points are at potential 0. Right, as you calculate the potential to minus Q and potential to this plus Q at all points, it will be 0. Right. Okay, and now for this plane I had to place also image charge. So let's put minus Q and the distances. Okay, so this minus Q will make sure that all the points on this lower sheet are 0. Okay, so this potential with plus Q and minus Q at all points will be 0. But no, it won't be 0 because there is potential to this minus Q also. So to balance that out, what do I have to do? I have to put again one more positive charge, positive image charge here. Now it will be balanced for this plane. Right? So because we have plus Q minus Q, okay, plus Q minus Q above this plane and minus Q plus Q below this plane. Now it will satisfy for this plane. But what about this plane? It will not be satisfied, right? Because for this plane you have three charges below it and one charge below it. So we have to put two more charges. So I have to put plus q here and then minus q here. Okay. But it will, if you look at now for this plane, it will not be satisfied. So basically, we have to keep on going. Okay, alternatively, minus q plus q, minus q plus q. Okay, and when we place that configuration, plus q minus q. Okay, so we have to do this kind of arrangement. Only then we'll be able to satisfy this configuration. Okay, so that means we had to place an infinite number of charges, but at what distance? What will be the distances? Let's see the distance from uh, original charge. Okay, original charge. So the distance will be original charge. Now this distance is L, right? Now what about this distance? This distance will be, now as you know, this is L by 2, this is L by 2, and the first image, because this was the image for this charge, right? So this is at a distance of L, and this is L by 2. So this will be at a distance of 3L by 2, right? From the plane. But what about from this charge, image charge? Okay, because we have to calculate the distance from the original charge. So that will be 3L by 2 plus this distance, that will be plus L by 2, that is 4L by 2, or you can say 2L. Okay, so first charge was placed at a distance of L from the original charge. Okay, and the second charge at a distance of 2L. Similarly, third charge will be at a distance of 3L, then 4L, and so on and so forth. So the option number, an infinite number alternating at a distance of NL, where n is an integer. Okay, correct. Now let's go on to final problem. In the method of image, suppose a point charge q is placed near a conducting wedge with an opening angle alpha equals to pi by n, where n is an integer. How many image charges are required to satisfy the boundary conditions imposed by the conducting wedge? So, conducting wedge like this. So like this. Okay, it's a wedge. Okay, I have in general, they're saying that it's an edge with an angle, opening angle alpha by 2. So this is a conducting plane, and this is also conducting plane, and the opening edge is pi by n. Okay, and if I put a image charge here, so this is my image charge, sorry, real charge. Where should I put my image charge? Okay, now let's do some generalization. So we know, suppose if I have two planes perpendicular, so no, sorry, one. Okay, now this is a plane, and whose angle is, you can see the opening angle is pi. Okay, just grounded. Opening angle is pi. Then we know when we put image, real charge here, its image charge is at minus q. Okay, with the distance same d, right? So that means when the opening angle is pi, my image charges. How many image charges? Only one image charge. Okay, only one image charge is required to satisfy the boundary conditions, right? Now let's do. If I have to, uh, let's make. If I have my configuration like this, when angle is equals to pi by 2. Okay, if I place my charge here, you then I have to satisfy the boundary condition, right? This is grounded, this is grounded. Actually, this kind of problem comes in TFR, so this is equal to 0 also. Now for this charge, I have to place my image charge. So let's put my image charge so that I satisfy one should be here and one should be here, and right. So this will satisfy my boundary conditions. No, I have to place one more. So positive 2 here. So this configuration of image charges will satisfy the boundary condition, because the potential at suppose any point, suppose this point. Okay, if I calculate the potential at this point due to all four charges, this is same distance, this is same distance, so potential will be 0. Similarly, if I take any potential here, the potential due to this potential, so due to this charge and this charge would cancel out, and the potential due to this charge and this charge would cancel out. So this is the configuration. So I had to place how many charges? How many image charges? When angle was pi by 2, the number of image charges are 3, right? So if you generalize now, if I have suppose pi by n, okay, pi by n, okay, I'm now generalizing. So it was pi by 1, then pi by 2. Now if I have pi by n, it seems that whatever n is in the denominator, it's let's see, will it be 2n? No. Will it be n? No. Will it be 2n minus 1? Okay, let's see, 2n minus 1. if n equals to 1, um, if n equals to 1, okay, pi by n, what's pi? Um, pi by, no, it doesn't seem satisfied. No, 2n, sorry, it's 2n minus 1. 2n minus 1. When n equals to 1, yes, it will satisfy, it will give me 1. When n equals to 2, 4 minus 1 will give me 3, yes. Now, what about this? So 2n minus 1 will give me the correct answer for every opening n. So 2n minus 1.